Hi, my name is Yulin Zhang. I'm going to talk about cover combinatorial filters and their minimization problem. This work is collaborated with my advisor, Dr. Dylan Shell. To motivate this problem, let's consider a robot patrolling in a house. This robot has two modes. It can either drive or fly. The flying mode allows the robot to fly over obstacles and rough terrain, but it generates a lot of noise. The driving mode allows the robot to move quietly. Here we're going to use a filter which has a graph structure to output the appropriate modes for the robot. In this filter, it creates a state for every possible location, and each state is colored as blue if the robot can choose to fly at that location. It is colored brown if the robot can choose to drive, or colored both colors if both modes are applicable. In this house, the robot must fly over the water spills in the pantry and the grass outdoors. So we color the front state representing the front yard, backyard, and pantry as blue. And in the bedroom, the robot must drive to keep quiet. So we color the state representing the bedroom as brown. In all other places, we color them both colors. The robot is initially located at the living room. It is installed with an ambient light sensor to sense the change of brightness. This measurement allows the robot to estimate where it is and output the appropriate modes. Now we get a filter to output the modes for the robot. In this filter, the sequence of measurement that can be traced in the filter is called a string, and the set of all strings that can be traced in the filter is called its input string. This particular filter is a naive filter because it creates a state for every location, and it maintains all outputs for each string. When we are trying to use this filter, we only care about just one valid output for each string. It may not be necessary to keep one state per location, and it may not be necessary to maintain all outputs for each vertex. In this work, we are trying to find a minimum filter that has the fewest number of states and satisfy the following two properties. The first property requires that all input strings from the original filter must be able to be traced in the minimizer. And the second property is called the consistent output. It requires that the output of those strings in the minimizer must be consistent with some output in the original filter. If a filter satisfies both these two properties, then we say that filter output simulates the original filter. You may notice that filter minimization problem is very similar to automata minimization. Both filters and automata have an initial state and deterministic transitions, but they are different in terms of their output. The automata choose to accept a string or not, while filters have a slightly richer output set. They assign outputs to every string. For automata minimization, we cannot choose to accept a string that crashes on the automata. But in filter minimization, we can assign any outputs to the crash strings. This gives us extra degree of freedom. It turns out that it is NP hard to minimize a filter by leveraging such degree of freedom. Let's think about how to minimize a filter. One of the most popular approaches used by the existing work is trying to merge the states. Here is an original filter with 8 states. It's trying to merge the states with the same color. We first merge the pink, then the red, and finally the purple. We get a minimizer with 4 states. But are the merging operations enough for us to reach a minimizer for any input filter? The answer is no. Here is an example. We modify the previous example by adding extensions to W5 and W7. Now we cannot merge W5 and W7 because if you do that, you will get a filter which has inconsistent output for string AAC. Here AAC outputs cyan, but this cyan is not a valid output in the original filter for AAC. As a consequence, we cannot merge the 3 pinks. Instead, let's just consider merging 2 of them. Together with all other mergers, we can get a filter with only 7 states, but this filter still has inconsistent output for AAC. If you try all different ways to merge, you will find out that there's no way for you to reach a filter with 7 states or fewer by just the merging operations. Now let me show you a different way. We are going to first split W6 into two, one with incoming edge labeled A and the other one with incoming edge labeled B. And we are going to merge the first part with W5 and the second part with W7. If you do this, you will get a minimizer with 7 states. And what we learn from this example is that to reach this minimizer, both merging and splits are necessary. So to minimize a filter, we need to consider both merging and split operations. But what set of states they can be merged? We say two states are compatible if merging them will not introduce any inconsistent output. As a consequence, two compatible states they must agree on the outputs of all their common extension. By drawing an undirected edge between two compatible states, we can get a compatibility graph. If we write a merge of several states as a set, then the set of mergers become a collection of sets, and each set they must form a clique in the compatibility graph. We also call the collection of sets as a clique cover. In this clique cover, if one vertex is not going to be merged with any others, then it forms a singleton set. If one vertex is contained in multiple sets, then we interpret it as splits and merge. So for example, W6 is contained in two sets. Then we say W6 is firstly split into two, and one is merged with W5 and the other one is merged with W7. So now we got an intermediate representation to model the merging and splits, and which is called a clique cover. And this clique cover must cover all vertex in the original filter, and every set in the cover they must form a clique in the compatibility graph. In this paper, we are interested in practical filters that have a deterministic structure. But do we always get a deterministic filter from merging and split operations? Is it possible that we can get a non-deterministic filter from merging and splits? The answer is yes, we could get a non-deterministic filter from some clique cover. In this example, we choose to merge W1, W2, but we don't merge their children after A, W5 and W6. As a consequence, we will get a non-deterministic filter. The non-deterministic structure of this filter looks like an unclosed zipper, and to enforce determinism, we need to introduce constraints to close this zipper. So we call those constraints as zipper constraints. The zipper constraints requires that if you merge a set of vertex, then you should also choose to merge their children after the same label in some set. So here's another example that satisfies the zipper constraints. In this clique cover, we choose to merge W1, W2, and we also choose to merge their children after A, which is W5 and W6 in some set. So now, to minimize an original filter, we need to search for a clique cover that satisfies these three properties. In the paper, we have shown that there exists a solution with M states if and only if you can find a clique cover with M sets that satisfy these three properties. Those properties are created to ensure that the resulting filter to be input inclusion, consistent output, and to be deterministic. Now the filter reduction problem becomes a search problem on the clique cover. Later on, we will show that this search problem will be formalized into Boolean satisfaction formalism. This should not be a surprise because the problem itself is empty-hard. Previously, the filters we saw have only one single output per vertex. But in the motivating example, we are also interested in minimizing filters with multiple outputs for some state. And we call those filters as cover filters. Here is an example of a two-row, two-color cover filter where W4 and W5 can non-deterministically output red or blue. You may think about treating those red and blue as a new color called purple, and then use a previous approach to minimize that. But the more interesting case is to allow the minimizer to make the selection about the color. And this is semantically correct because it generates consistent output. But this extra degree freedom may allow us to get a much smaller filter. Another question is when to make the selection. If you choose the selection up front for each vertex and then merge and split, this may not give you a minimum filter because the minimum filter may require you to choose different outputs for the strings reaching the same vertex. And here is an example. If you choose the color for each vertex first, then the best filter you can get has at least 4 states. But the minimizer has only 3 states. It is obtained by merging and splits, and then color selection. So the algorithm must make decisions about the color selection together with merging and splits. For vertex single output filters, where every state has exactly one output, we can merge the set of states if they are pairwise compatible. But this is no longer true for cover filters, because every state in a cover filter is compatible with others conditioning on their color choice. And there may not exist a consistent color choice to allow you to merge the set of pairwise compatible states. So we generalize the compatibility relation to group compatibility, which does not only check every pair of vertex, but also any subset of vertices on their outputs of their common extension. And the compatibility graph becomes a compatibility simplicial complex. The filter minimization problem becomes a search problem on a minimum simplex cover. And this search problem may be interesting in their own right, but here we choose to encode them into set formalization. We create Boolean variables to encode the cover, and these properties on the cover becomes constraints in conjunctive normal form. This gives us a set problem which is parameterized by m. If we solve this set problem, then we find a solution with m states. To find a minimum solution, we initialize m to be the number of states in the original filter, and then decrease m to solve the corresponding set problem. And we repeat this until this set problem can no longer be solved. And the minimum m with a solution gives a minimum filter. Now we got an algorithm to minimize a cover filter. One of the questions we have in mind is how does this algorithm scale with the number of states in the original filter? To check this, we construct a filter for the robot to navigate in this square environment. The robot must go to the pink cell and take the left exit, or go to the green cell and take the right exit, or go to the cell with 2 colors and pick either left or right exit. We collect the time being used to minimize this filter. As we increase the number of states in the filter, the time being used to minimize this filter grows exponentially, and most of the time has been used to construct the zebra constraints. With a closer check, we find out that there's no zebra constraints being constructed. All the time has been used to examine the compatibility simplicial complex. Here is the dirty laundry. In the worst case, both the size of the compatibility simplicial complex and the number of zebra constraints can be exponential. It gives a very inefficient set formalization. Our subsequent work studies efficient formalization of this problem and proposed practical treatments of the constraints. Another question is how does this algorithm scale with the number of outputs? We generalize our previous 2-row 2-color cover filter by adding more rows, and each row has different output. Here W4 and W5 have all the colors from all different rows. To minimize this filter, as we increase the number of colors, the number of zebra constraints and the time being used increase only linearly. As a conclusion, we re-examine the existing treatment of classical filter minimization, and we find out that both merger and splits are necessary to find a minimizer, and we need to enforce determinism explicitly. We propose a single-step compatibility relation and use a click cover to model both merger and split, and we also use zebra constraints to enforce determinism. Now the filter minimization problem is converted as a search problem on a minimum click cover that satisfies some property. And we generalized this minimization algorithm from classical filters to cover filters. This concludes my talk. Thank you.